So welcome to the application of methods in design practice session. My name is Dietmar Göhlich from the Technische Universität Berlin. I'm sharing here our activities on product development methods and mechatronics since 2010. And prior to that, I have 20 years of industrial experience in the design of automobiles in Germany. So I hope I have some background on application of methods. And I'm very happy to introduce our first speaker, which is Matthias Eisenmann from the Karlsruhe Institute of Technology. He was a student at KIT there, and now he is a scientific assistant, a research associated at the famous Institute of Product Engineering at the KIT. So please start the video now on his presentation on identifying reasons for lack of method application in engineering design practice and interview study.
I would like to start my presentation with a quote of one of the interviewees. That is, I believe that it's very important for the method that the designer realizes it gives me added value when I use it. And if he doesn't have that feeling, then he won't use it. And that is an excellent example of the viewpoint of practice on design methods. Previous investigations identified multiple possible reasons why design methods are seldom applied in design practice, even by experienced designers. Those reasons range from constraints of time and resources, over low usability, up to missing responsibilities for the transfer of methods. But what those investigations often leave out is that the designer has to have a need for the method to wanting to apply it. So that is what we focus on in our research. Non-routine situations are situations that are connected with a need for methodological support. So those are the situations that we want to investigate. And despite of several investigations that are part of the state of the art, there still remains a research gap. That is, it is unclear when exactly those situations occur in practice and how design engineers cope with these kind of situations. For our semi-structured interviews, we chose 10 experienced design engineers from 8 different German firms. And after those interviews, we transcribed the recordings to enable content analysis, and those contents were interpreted and clustered to gain the results that are presented in the following. In our content analysis, we identified 6 different causes of non-routine situations that you can see right here, and some of them are already well described in literature, such as the ill-defined task or the time pressure. But a new aspect that we found in our study is the system under development that causes with its intricacy that you can forget some aspects during design, and that poses some interactions with itself and the environment that make non-routine situations occur. We also identified 3 different clusters of strategies that experienced design engineers apply when confronted with non-routine situations. First one is generating informations that relates to situations when there is missing information. In some cases, this information can be gathered by either analyzing existing data of similar systems or by generating new data using prototypes and simulations. The cluster of method application describes different applications of methods. We found different types, and those are methods prescribed by the company and others voluntarily applied design methods or at least method step. And additionally, 2 participants showed a high level of methodical competence by adapting methods according to their company's needs. But the most significant cluster is the one of experience that is represented by the following quote. As an engineer, you should listen to your gut feeling, because this gut feeling represents an incredible amount of experience that you can't grasp. So I'd rather listen to an experienced engineer with his gut feeling than to an inexperienced engineer with a calculation. As we've seen before, there are different dimensions of causes for non-routine situations, and those are grounded in a lack of product knowledge or a lack of process knowledge. And the strategies that we have seen are in the part of generating information and method application that address either one of those dimensions, but the use of experience or the gut feeling can address both of those dimensions and the room in between. So our conclusion is that the experience of the individual designer as well as of the design team reduces the formal use of design methods in engineering design practice. So thank you for your attention and feel free to ask any questions.
Okay, so I think we lost our chair again. Okay, he's here. Hello, can you hear us?
I cannot. I see you, but I.
Okay, we can hear you.
Can you hear me now?
Yes. Do
Okay,
you hear us?
sorry. I lost the connection in between, but we can continue the session anyhow. And I would like to introduce the second speaker, which is Mr. Sindre Eikevåg. He is a master's student at the Norwegian Institute of Science and Technology, and he is going to speak about designing an experiment for evaluating seating positions in a Paralympic rowing. Please.
Designing an experiment for evaluating seating position in Paralympic rowing. Hi, and welcome to the presentation. The paper presented is written by myself, Sindre Eikevåg, Andris Kvam, Magnus Kjærnet Bjølseth, Jørgen Falck Erichsen, and Martin Steinert. This article presents the design of an experiment for identifying and evaluating various seating positions in Paralympic rowing by using a rowing ergometer with a modified seat. Results indicate that changing seating position has a substantial impact on rowing performance. Paralympic rowing is divided into 3 classes, depending on impairment. This article focuses on the PR1 class, where the athlete uses a stationary seat, having minimum to no trunk function. As seen during the 2016 Paralympics, every rower in the PR1 class are used in their own custom design. The aim of this experiment was to identify better seating position for a specific Paralympic rower on a rowing ergometer by measuring and comparing heart rate, lactate, and stroke rate per minute. The design of the experiment also includes the design of equipment necessary to conduct the experiment. In this case, a specialized seat allowing seating position to be quickly modified. When designing high-performance sport equipment for Paralympic athletes, there are many unknowns for the designer to consider. The design challenge is an optimization task per individual athlete. The exact amount of muscle activation, which muscles and with how much force per individual is not fully known. This causes complexity to the design problem, where we do not have full control or knowledge about all influencing variables and how they impact performance. Therefore, high-performance gear cannot be optimized in a straightforward fashion. Instead, we propose and test a heuristic and iterative approach that combines physical testing with user integration. Extremities of the adjustability was pre-tested with the athlete, both for the steep and shallow angles. This formed the design limitation at both ends, together with the athlete's range of motion and the maximum adjustability of the seat. Position 1 is the benchmark position used by the athlete in the competitive skill. Position 3 is close to the limitation of the athlete discovered during pre-testing, and position 2 are in-between position. An experiment has been designed to identify rowing performance at various seating positions. The experiment procedure was worked out in cooperation with the athlete's coach, and physical therapist. After a 10-minute warm-up at low intensity, 3 sets of 4 minutes at increasing power targets, 50, 70, and 90 watts, were performed with all 3 seating positions on the Concept 2 rowing ergometer, using resistance level 1. To experiment with different seating positions on the rowing ergometer, a custom seat was designed with requirements specific to this experiment setup. Testing was conducted on a controlled environment on land, as water, wind, underwater currents, and other conditions would add to the many variables and unknowns. The design of the equipment was initiated by sketch drawings of different concepts fulfilling the design requirements. Simple prototypes were created for comparison. Using these prototypes, the necessary number of adjustments and the size of the relevant forces were determined. The final seating position consists of 3 parts: seat back, seat plate, and tie support. The equipment facilitates a wide range of seating positions suitable for the athlete and could quickly change from one position to another. During the experiment, the seat back was adjusted downwards, making the angle shallower at consistent intervals. The results differ greatly between seating configurations. At 90 watt target power, the percentage of maximum heart rate was reduced from 87% in position 1 to 77% in position 3. When comparing position 1 and 3, the lactate levels also dropped by 54% and the stroke rate by 14%. From examining the results, it is evident that adjusting the seating position had a major impact on the Paralympic athlete rowing performance, despite the limited amount of data. However, the optimal seating position cannot be concluded to be found. More testing at multiple days with the athlete is desired to fully understand the individual biomechanics at work. If you're interested in this topic, there will be coming several additional publications in the near future. So follow us, and thank you for your time.
Okay, we lost our chair. Dorian, can you maybe help?
I think we should wait a second or a few for Professor Göhlich to come back, and if not, we can go to the next presentation.
Yes, he's here. We've lost him again.
Yeah, this is interesting. Yesterday, Professor Weber was all day with us without any problems. Today also Professor Weber has a problem, so it is quite uncontrollable. Welcome, Professor Göhlich. Please continue to chair.
I'm trying my best, so you can hear me.
Yes.
So I think we're ready to receive the third presentation on design of an active seat suspension for a passenger vehicle. Please.
Welcome to the presentation of the paper titled Design of an Active Seat Suspension for a Passenger Vehicle. After a short introduction, the presentation will discuss the requirements of the design of the suspension system, analysis and evaluation of proposed concepts, choice of the overall concept, and detailed mechanical design of the chosen concept. Introduction of seat suspension systems promise to dampen vertical vibrations of the vehicle, thus reducing health risks for the passenger as well as increasing the ride comfort. 3 types of suspensions are suggested: passive, semi-active, and active, where the active systems promise best performance but at a high cost compared to the other 2 proposed solutions. The goal is to propose a design of an active seat suspension, but with a favorable price-to-performance ratio. Several design requirements are given. some of them are hard defined, such as required load, speed, or acceleration. Some are somewhat loosely defined, such as low cost and high stiffness. Suspension system is divided into 4 major subsystems, including carrier structure, source of force or the actuator, spring, and the damper, where the first 2 take majority of available volume and have highest impact on the overall cost, and will therefore be in the focus of the initial analysis. The second 2, the spring and the damper, will be later added during the more detailed design. 10 concepts have been evaluated for the carrier structure, including linear guides, several types of scissor mechanisms, and various other lever-based mechanisms. They've all been evaluated based on the initial requirements. For the seat actuator, 16 concepts have been proposed, analyzed, and evaluated, again in accordance with the initially given requirements. These include several types of spindle-based actuators, hydraulic actuators, etc. Overall concept of the active suspension system for the automotive seat is developed by combining one carrier structure concept and one actuator concept. 2 overall concepts are suggested for further development. The first one is based on a dual Scott-Russell mechanism for the carrier structure and a screw drive-based actuator. It is assessed that this concept will have the best mechanical properties, particularly from the standpoint of stiffness. But however, it will be also characterized by the high costs due to necessity of the linear guides. It is proposed to use this concept to develop an experimental type of seat suspension system. The second overall concept, is based on the Saros mechanism with a diamond-shaped actuator. It is assessed that this concept will have low cost due to being designed from levers and joints. However, the same will result in somewhat lower stiffness, which may become a problem during the application. As such, this concept, being low cost and thus suitable for mass production, is assessed as a candidate for the actual in-vehicle application. The first proposed concept, the one based on the Scott-Russell mechanism, has been designed in more detail to be suitable for implementation with the existing shaker test rig, which generates vertical vibrations emulating the ones existing on the actual vehicle. This concept, once developed and installed, will enable this test rig to be suitable for investigation of the impact the active suspension system has on the actual ride comfort. Saros mechanism is thus proposed to be used as a basis for the mass production solution. Thank you for your attention.
Okay, thank you very much for this presentation. Our final presentation from Mr. Ilya Yuskevich, the systems engineer in aerospace and automotive in Paris. And he's going to talk about a discrete event simulation model for driver performance assessment, application to an autonomous vehicle concept design optimization. Sorry, please.
Hello, everyone who has connected to this presentation. My name is Ilya Yuskevich, and I'm a PhD student at University Paris-Saclay and at IRT Systemics. I am happy to present you today our work, a discrete event simulation model for driver performance assessment, application to autonomous vehicle cockpit design optimization. Here is the problem that we are trying to solve. As many of you probably know, state-of-the-art self-driving cars cannot be operated fully autonomously in all driving conditions possible. To overcome this difficulty, so-called dual-mode ADS-equipped vehicle has been proposed. ADS is Automated Driving System. So how the system is operated? It can be fully autonomous in some parts of the road, but in some other part it must be driven fully manually, or just partial automation is available. This is so-called operational domain. So what dual-mode ADS-equipped vehicle impose on the design of a cockpit? Basically, it brings some additional elements of indication and control. For example, we must inform user that ADS is on the L2 level. We should also inform user about the road conditions. AD is available in this case. Here we have new control elements, in this case, switchers between levels of automation. Some additional signals might be necessary, such as we can imagine some voice message that warn user that AD zone will be finished in 2 kilometers. So what is the problem? The problem is that we have added complexity on human-machine interaction, which can bring overload of the user, and this can have some serious safety issues. To figure this out, we have developed a discrete event simulation model that is based on two approaches. One is famous multiple resource theory of weekends that basically postulates that human has multiple channels of perception, and if we send different information through concurrent channels of perception, we can perceive this information at the same time. The other approach is task analysis. As an example, this paper in which they have analyzed the performances of the military helicopter operators, they have decomposed the complex operation tasks into elementary tasks and assigned different workload values for each of those tasks. So this is our discrete event simulation model. We have 3 independent agents, ODD, ADS, and driver. Each of those independent agents has its own state machine and functions that are random processes that generate events. Those events can change the state of the state machine of the agent, or they can trigger tasks. Those tasks go to the perceptive model of a driver, which basically represents this picture, the multiple resource theory of weekends. We have several parallel perception channels. Tasks are scheduled in this module, and what we want to check is that users shouldn't be overloaded at any moment. On this slide, you will see results that we may achieve with our model. An input for our model is an Excel file with the function architecture of a cockpit that we are designing. It consists of elementary tasks. This is the simulation model, and this is an output of simulation model. Top chart shows state of ADS and ODD. Green line shows automation levels available at a given moment. Red line represents the state of ADS. These are dynamic performances of driver: perceptual workload, cognitive workload, and eye of the road time. If at some moment we have large values, it may indicate that we have safety issue here. This normally happens when we have shift of the state. In this case, we may want to redesign our function architecture and repeat simulation. That's how iterative design optimization happens. We will invite several dozen people to test our cockpit prototype. During this user testing, we will also validate our simulation approach. We will control gaze direction and electrodermal potential. Conclusions. The contribution of this paper is that we took existing approaches and applied it to state-of-the-art problem. We created a simple model that is low cost, easy to interpret, and suitable for early stage design optimization. Our model parameters will be tuned during user testing. Thank you for your attention.
Okay, our presentations are over, And as I see, there is no chair right now, but you can, but everyone participating can ask questions in the chat or until he returns back. So he's here.
Okay, I'm back. Sorry, but I can't help it. I have not seen any questions in the chat, or did I miss anything there? So
there is one question right now.
okay. So I think this is a question for the fourth presenter. Would you want to respond to that directly?
Yes, sure. So this is a simulation approach. So we calculated cognitive workload with our method, but we're gonna validate the results with electrodermal potential and some subjective measures. So we will have a questionnaire. We will invite people to our facility. They will test our cockpit prototype, and then we will run some tests.
Okay.
Validate our approach.
Thank you for this clarification. I would have stated a similar question. So you're still in the process of validating your model. Yeah. But maybe you can explain a little. What kind of use case did you show in your results? What kind of driving situation was that?
So basically, we have some simple raw scenes, 5 minutes each. And during these scenes, user should turn the car to the fully autonomous mode, and then he should take over. So we have some takeover requests, like the autonomous driving zone will be finished in 60 seconds. So user should take actions, he should prepare, he should click the button. So this kind of scene. Of course, we have some also machines on the road and etc. But it's pretty simple.
Okay, thank you. I think I would like to go back to the first paper. Matthias Eisenmann, thank you for your presentation. I would like to invite you to maybe summarize again your findings in terms of what would be your recommendations for the community of academia product development methods, like me or like all the other colleagues.
All right, I try to make it short.
Yes.
I would recommend
the approach used was with.
Okay. Did you also hear that other question? Sorry. I would like to recommend that you should find out if the designer really has a need for the method. So a lot of designers have no subjective need for a method because they use their experience and other gut feelings and so on. So when validating design methods, you should focus on whether the designer did have a need for this method or not. That's like the bigger consequence of that. But I guess there was another question that was about how I differentiate the routine and non-routine situations. Well, in the interviews, we asked them about situations that were hard to cope with, so that were not day-to-day business, but rather when they got stuck or didn't know how to proceed. And in my opinion, that's the kind of situations where you have a objective need of methodological support. So I hope this answered the question of the chat.
Okay. There's another question. How do you differentiate routine and non-routine design?
Try to answer that one right when
I was out.
of
okay, sorry.
No worries.
Okay. I would like to pose a question to the second presenter on your designing a seat for rowing. I did not quite catch why you didn't go with this seat design directly into some experimental verification. It seemed so obvious. I mean, your results were so striking, and the design modifications seemed pretty rather straightforward. Why didn't you go directly into some testing?
Yes, after we finished up this paper in November, we went straight into testing with the assembly. So the testing has been conducted now, and we are currently working on a second publication on this topic. If that answers your question.
Yes. Okay. And there's another question. You can read it from Dorian Marjanovic. Can you read it and respond directly?
Yes, we have a question from Dorian. How do you determine the muscle forces? Seems like the muscle selection simulation is essential. Yes, the first part of this publication is all about identifying the limitations of the athlete and how to set up the experiment. Like I said in the previous question, when we moved on, we looked at the muscle muscle skeleton, sorry. Yes, the muscle skeleton is essential when testing, but the approach of this method is that when you're working with Paralympic athletes, everyone is different. We don't know how to adjust according to each needs. So by using an iterative approach and testing several different seating configurations, we could identify athlete specific the right configuration. I don't know if that answered your question or
Thank you. I'm fine with the answer. I was a little bit concerned reading your paper about how you get the forces for simulation. That was.
Yes, we did an iterative approach, practical approach to this subject.
Okay. Okay. Thank you.
Can you again hear me?
Yes.
Okay, I'm trying to continue as good as I can. I would like to pose a question on the design of an active seat suspension to Mr. Hoić. First of all, I would like to answer to get some information. What is your use case? What kind of road situation do you want to tackle with your active seat?
We have several road types.
Mr. Hoić, are you still in?
Yeah.
Just a second.
Did you hear my
you hear
question?
me? I heard the question. Can you hear me? Can you hear me or?
I can hear you.
Obviously, I seem to be in, but I do not hear any answer.
Okay, it seems that some of you can hear me and
Dorian,
some
am I
of
still in
you
the session?
cannot.
But nobody else is?
It seems that chair cannot hear me, but the rest of you can.
I can hear.
Okay. So I try again, Mr. Hoić. Did you get my question on your active seat suspension presentation?
I got the question. I'm not sure if you can hear me now.
No. Okay. Then I would like to ask another question on the seating positions for the rowing to Sindre. Are you in there? Can you hear me?
I can hear you. It might be the same problem here. Can you hear us now?
Yes, I can hear you.
Yes.
Okay.
Okay, so how would you like to proceed?
Let's go in the order. As Professor Dietmar has asked the question, Matija, please go on, and then there was a second question for
Okay.
Sindre.
Okay, so what we have is actually several road types which were used to evaluate the capabilities of individual vehicle suspension system. Several dozens of people were participated in the initial investigation, where the goal was to determine how successful individual suspension system of the entire vehicle is with respect to road profile. These road profiles typically simulated about 10 minutes of drive, and were to some extent they were quite rough. Namely, initially when we tried to use a typical road, then there would be maybe one bump per the entire drive, and it will be difficult for the participant to evaluate which suspension system is better. The idea was that once we upgrade this shaker test rig with the active suspension system, we would repeat all of the experiments, if possible, with the same participants, and then see how much of the improvement can be achieved when active suspension system of the seat is used. I'm not sure if that answers your question.
To some extent, yes.
Yeah, yes, I'm here, but I didn't get the question, only that you had a question for me.
Professor Dietmar had a question for you. Before.
Yes, but it didn't say what the question was, only that you had a question.
Professor Dietmar, you had a question for Sindre. Seems he had a... Oh, Professor Dietmar has gone. Okay, then a question for Matija. Matija, I'm not quite sure if you have heard it, seen it, but regarding your development of the passenger seat, I would say that you have been considering only the mechanical part. I would say that nowadays development of passenger seat starts with the user requirements. Are they considered in your development at all, or how they are considered?
Well, the user requirements in this case are a bit problematic with respect that user wants comfort. However, the problem is how to define this comfort, what is comfortable enough or not comfortable enough. So what the goal was is to design a system which can be shown to the potential customer, where he can actually sit and try it and say if it's good enough for him. This is a bit of a problem, partially because user requirement at this point is a bit ill-defined, because it is a requirement on the passenger seat for an autonomous vehicle, which at this point are still not used widely. So the passengers still need to come up with their requirements on what they would like to do and what kind of requirements they have. It is assumed that the passengers would like to maybe read a book or do some work, answer some emails and similar. And they will need the ride will have to be comfortable enough for them to conduct these activities. But the question remains, what does it mean to be comfortable enough?
I would like to ask another to Matthias Eisenmann if he can hear me. Okay. Now you state that that you find different levels of method application. How do you do that? You just ask them on the level of method, verify that really into their.
We got that information only from the interview, but according to the highest level of method application, we found out that 2 of the participants really developed methods for their firm, for their company. So that's not been validated by looking into their work, but by asking deeper and digging deeper. So I'm afraid he has left us again.
Oh, I'm sorry. I'm always losing the line. I'm now back in, but this is really terrible. Does anybody else in the room have some questions? Because if I ask and then I drop out, this is not really helpful.
Cannot hear you, Professor Marjanovic. We cannot hear you.
With my mic, easier for you. I'm wondering why you haven't heard me.
Now we.
Yeah. So I would like to continue discussion with Matija about user requirements, and if we put apart the requirements regarding appearance and size, weight, etc., then there is one part which is really important, which user cannot define, but the comfort is defined mostly through the capability of damping of the vehicle vibrations through the seat design. So what is really the difference between high-class car and the low-class C or middle-class C is the damping capability, what seat can damp. The vibration the seats are damping, so the passenger doesn't feel these vibrations. And if you want it down to the bone, these vibrations, if they came to the bladder, implicate some effects that require driver to stop quite often. So what do you think, have you taken into account such requirements?
Initially, for the part of the project which was related to the suspension of the vehicle, that's what the shader test rig was built. What the immediate goal was to determine the perceived comfort. This was intended for a mid-class vehicle, so price-performance ratio is quite important. And the question was, to put it simply, what is the highest vibration that can occur and that the passenger will not immediately sense? Of course, on the long run, for long rides, passenger will eventually be aware on the comfort of the vehicle, but immediately at a given point there's a threshold of vibrations under which they will not be sensible. Once that was investigated, that's a topic of a separate paper. We continue with design of this active seat suspension system. Again, price-performance ratio is quite important for the mid-class vehicle. Some rough calculations said that the introduction of active suspension system would increase the cost of the vehicle by 10 to 20%, which would not be acceptable for a mid-class vehicle. So the goal is to see whether we can design an active suspension system for a seat, then which would be cost effective and be capable of suppressing vibrations sufficiently for the passenger to notice the difference between a regular seat and a seat with an active suspension.
Thank you very much. I have a question from. Okay, go on, Professor Göhlich.
Ask another question. Approaches focusing on the vertical vibration of the seat. Role. How does that feel for the passenger? One component which is compensated, but the others are still there.
At this point, we don't know. The input for the project was that the vertical vibrations are the main cause of discomfort for the driver, and that the pitch and roll are less significant because they do not occur with the occurrence with which the vertical vibrations occur. Also, we can the second question that exists is what can we do about them? We see here that even a single axis design is quite complicated and will be quite costly. Now to design a suspension system which would also compensate for pitch and roll, that is something that is again quite beyond the limits of the acceptable cost, and also would be beyond the limits of available volume. Namely, currently existing seat suspension systems are used in trucks and similar commercial vehicles.
Tractors.
Tractors.
They're very successful in tractors.
Yes, and in all these cases, there's quite a lot of room between the chassis and the bottom of the seat. But for a passenger vehicle, we're talking about maybe 100 millimeters or something like that. And so there's quite a little room. There's quite a lot of constraints related to cost. So everything was limited to vertical axis as the main source of discomfort when talking about the influence of vibrations. Ultimately, it would be ultimate solution would compensate for vibrations in all directions, but it doesn't seem feasible for a mid-range passenger vehicle.
Okay. I have a question for the Ilya, if you can hear me. The question would be, you basically said you have a manually optimization. What it means really, and what is not clear is you compare it to the base design. And what is the base design in your case?
We don't really have base design. Well, there is a base design that was created by ergonomists, like professionals in the field. And then there is this simulation tool that can help them to assess maybe there are some problems in certain moments, maybe there is some overload and potential risks in terms of safety. Also, we have several profiles of users. So this user interface should be adaptable for different psychological profiles of people. So we have kind of novice user that likes to try different new things, and there is a conservative user that is more traditional and don't like to have a lot of new features. So we will compare first the profile, the configurations, the functional architecture that was proposed by human designers, and we also compare this to psychological profiles of potential users.
We lost you.
I'm here.
Okay.
How many users do you going to include in your testing, which you envision for verification purposes?
It's about 50 people.
50, okay. That'll take some time.
Sure, especially now.
That's
We postponing.
I have one question to Sindre. I was thinking later, and I was wondering, the rowing simulator is of course different from real rowing because you have only 1 degree of freedom instead of 2, right? In fact,
Yes.
Results.
I don't understand the question. Of course, there are. In normal rowing, when using a sliding seat, there are 2 degrees of freedom. Like
No. I'm talking.
About how the arms only have 1 degree of freedom. Sorry, I'm struggling to hear you.
Sorry, I still have a bad connection.
We have quite a lot of background noise from somewhere. Okay. Oh, we have lost our host again. I think it is quite hard for him under this condition to share the sessions. Now he will be back. I apologize in behalf of the organization of the Design 2020 conference for this. It's not usual and it's quite uncomfortable for all, especially for Professor Dietmar Göhlich. It's really not easy for him, but this is hard to. Basically, we cannot overcome this, and it is beyond our possibilities and also beyond Professor Göhlich's possibilities. Today we had more than 295 connections, people, unique participants, and however, most of them worked, not most, almost all worked quite fine. So I don't know what's going on. However, I think we should close this session and then you can continue. Please join us on the Gather, and then we can continue this discussion on the Gather Town, which will start quite soon.
Okay.
Oh, you are back.
Yeah, thank you very much for Dorian for overtaking. I'm so sorry. Once I get the connection, it's okay, but then I drop out, and I'm here at the university where I usually have a very good bandwidth.
It's not up to you. I was just saying that it's not up to you, nor it is up to us.
Yeah.
As I said earlier, Professor Weber yesterday worked without any sign of any trouble. Today he has the same manifestation as you have. He's dropping out almost every minute or something like that. I don't know what. I believe we cannot do anything about this from our side, from the organizer side, or from your side. Basically, this is on the internet traffic and the Hoping website, where they declare they can accommodate 100,000 users. That's nice to hear, but sometimes, obviously, technology does not behave as we are expecting. So since the time is out, I would like to thank you, Professor Göhlich, for handling this session and for chairing this session under this, I would say, quite uncomfortable conditions. And also, I would like to thank to all participants and also to Ivan Čech, our helper. Thank you. Hope to see you at Gather Town and hope to see you tomorrow on the other sessions of the Design 2020 conference. Bye-bye.
Bye-bye.
Bye.
Bye.